Mm-hmm. So we have 9 TVs. 2 are defective. And so let me get the other details. 9 TVs, 2 are defective. If 2 are randomly selected. All right, so we have 9 TVs altogether. 2 are defective. If 2 are randomly selected, find the probability that both work. Then find the probability that one works and the other one doesn't. So let's look at A. Once again, we have 9 TVs. If 2 are defective, that means 7 work. All right. So we want the probability, let me do it like this, that when you, let's see, first TV works and second TV you choose work. All right. So now when we look at the probability of getting a defective TV, that's 2 over 9. Probability of getting a working TV is 7 over 9. Now, when I look at the probability of the first one working, that is going to be 7 over 9. But then we're going to multiply it times the probability of the second one working. Now, remember, if I choose one out of this group right here of 7 out of 9 TVs, if I choose one, then that means I have 6 TVs that work, that are working, that are left. And I have 8 TVs that are left. So the probability of getting a working TV after I've already chosen a TV that works will be a 6 out of 8 chance. And so you would multiply those two together. And I could have reduced first. 21 over 6. I could have went some more. I could have did a whole 6. That's right, because 3 times 2. 3, so that's 7 out of 12. So it will reduce down to 7 out of 12. So I don't know if they wanted, let me see, let me go back and go to the problem. See if they want decimal. Oh, it's around the 3 decimal places. So let's see what the decimal is for that. And that would be 0.583. All right, questions on that first one on A?
Nope.
Thank you.
Not a problem, not a problem. So B is the probability that one works and the other one doesn't. All right, so for the next one, we know what the probability of the first one working and the second one defective. So we just saw the first one working means it'll be 7/9. Now the second one being defective will be 2 out of 8 because I still have 2 TVs that are defective out of the group. But if I've chosen one TV, then that means that there are 8 left. So multiplying those together, and like I said, we don't have to reduce the fraction because they want a decimal. So that's going to be 14 over 72. 0.194.
That's where I've been messing up. I haven't been taken. I've been taken away from the wrong place on part B. I've been taken away from the top and the bottom.
Gotcha. Yeah.
Times 2/9.
All right. Questions? Any questions? Hope that helped. Hope that was all right.
I believe I got it.
Hold on. 6. Oh, we're looking at 7. Okay, so let's look at 7.1. And I think we'll be able to finish it. If not, like I said before, no rush. We'll get to the rest of it next class. Oh, I put it wrong. Not distribution. Sorry about that. It's density. All right, so probability density function is where we're going to start this section. We're talking about properties of normal distribution. That's your bell-shaped curve, and we talked about that before. We're going to get more into the application of that in this chapter. So the probability density function, also known or shorthand written as PDF, an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. Total area under the graph must equal to 1, and the height of the graph must be greater than or equal to 0 for all possible values. All right, so a continuous random variable is normally distributed or has normal probability distribution. Those two mean the same thing, normally distributed or normal probability distribution. If its relative frequency histogram has the shape of the normal curve. And that normal curve is that bell-shaped curve that I showed you earlier. So we'll look at that again.
Sir, how do you get the middle one? I'm sorry.
The middle one?
Yes, sir.
What you mean?
How do you get the the top of the curve?
You talking about up here?
Yes, sir.
Oh, well, that's just the shape of it. So that's going to be where the mean is.
Mean. Okay.
Yep. That's going to be your middle value, or the height of your curve is going to be the mean.
And the other ones are the medians?
No, not necessarily. Your information, the bulk of your information is going to be around the mean. Remember, means your average. So normally, if your data is normally distributed, then the bulk of your information is going to be near the mean. So that's why the bulk of your information is here. And then as you go away from the mean, whether it's to the right, which is greater, or less than, which is to the left, less and less of your data will be there.
So mean is the middle.
Right. Yep.
Thank you.
hmm And that's going to be the peak of your data as far as the height is concerned. All right. So here we have our mean. And if you were to, in the middle, we have our mean. And when it comes to your normal distribution, as I just mentioned to your classmate, in the middle will be the mean, the average of your data. And then we have inflection points here, and inflection points are say graph, I can say curve. All right, so inflection points, and I don't even know if they even do any more with that than just pointing them out. I don't really think that they actually have an application as far as this section is concerned, but they do point them out. So just in case they were to ask, what are the inflection points? When you add a standard deviation to your mean and then subtract a standard deviation away from your mean, that's what we have here. Those are your inflection points of your normal distribution. And those inflection points are points where the curvature changes. In other words, it goes from concave up to concave down. This is concave up, this is concave down. So when the concavity, curvature change. Normal density. Okay, we got like 7 points, so don't want to go too far here without making sure we're okay with the ones you have written so far. So properties of the normal density curve. The normal curve is symmetric about the mean, so that means it reflects. You have your mean in the middle, and then what's going on the right side of the mean is going on the left side of the mean. It reflects about the mean, and you'll see that relationship emphasized between these two sections of 7.1 and 7.2. Point two alludes to what your classmate had asked about. Your mean, median, I left off the end right there. Mean, median, and mode are equal. Has a single peak and highest point at your mean. So that middle point, the highest point is going to be your average, your mean. Don't forget your average is your mean. Stat name for your mean. Stat name for your average is your mean. And then third point, it has inflection points, which is already mentioned, but it's one of the properties. It has inflection points at your mean minus your standard deviation and your mean plus your standard deviation. All right. Area under the curve is 1. So when you go back to, I'll just write it right here. So when you look at our normal curve, everything under here, when you add it all together, all that is equal to 1. So if you were to, go from here to here, if this is 0.25, then you automatically know this is 0.75. Or if this is 0.3, you know this is 0.7. So everything under that curve is equal to 1. All right. All right, so the area under the curve to the right of the mean equals a half, and the same goes for the left of the mean. So that basically takes 0.2 and 4, well, really 1 and 4, put them together because we already know it's symmetric about the mean. I say that what goes on the right side of the mean goes on the left side of the mean, and everything under the mean is equal to 1, and your mean is in the middle, which is 0.2. So it's just taking those, making sure that you understand that 0.5 or half of your data will be to the right of your mean, half of your data will be to the left of your mean. All right, so as x approaches the graph, or x as x increases, sorry, the graph approaches but never reaches the horizontal axis. And when we talk about the horizontal axis, we're talking about 0. And the same goes for x as it decreases. So if you look at this graph here, notice I never connected these lines down here because your graph should never touch the horizontal axis when you're talking about the normal distribution. So it will approach the horizontal axis. In other words, it will approach 0, but never actually get to 0. I want to write like that. That's fine. All right, the last property, the empirical rule. We talked about the empirical rule before. Approximately 68% of the area under the curve is within 1 standard deviation of the mean. 95% of the area under the curve is within 2 standard deviations of the mean, and 99.7% of the area under the curve is within 3 standard deviations of the mean. All right, let me see if I can draw this. All right, so just wanted to give you that diagram, but I've given it to you before. That's your empirical rule. This is just a diagram that reemphasizes the three statements that came before the diagram. 68% of your data is within one standard deviation of your mean, 95% two standard deviations, and then 99.7% is within three standard deviations.
Sir, how do we put that to a math problem?
They will give you the mean and standard deviation, and but we've
Okay.
already done that before. That's coming out of previous. They're just telling you this is the property. This property
Okay.
still holds true. In other words, they would have given you because as far as finding the mean and standard deviation, they already feel like you're cool with that if you're at this point. So they would have given you the mean. Let's say the mean was 20, and well, let's say 100, and then 16. So your mean would be in the middle. Add 16 is 116. Add another 16 is 132. That process right
Okay.
there. Yeah. So that's more so of a review, just letting you know that property still holds true for this case. Let me see. Trying to see if they have any decent examples. I was just talking about. Yeah, because they don't even talk about. They don't even use the empirical rule in this section. They're just saying it's one of the properties. So draw a curve. Let's see. So they have the birth weights, and they really didn't have many examples. Really, that was the end of the section. Yeah. Anyway, they only have a few examples, so we'll do this, and then we will go from there. So we have birth weights of full-term babies are normally distributed with mean 3,400 and standard deviation of 505. So before we look at any questions, let's just make sure we're okay with that empirical rule chart that I mentioned. So we know in the middle is going to be our 3,400. That's our mean. So when we look at the right side of the mean, going to add a standard deviation. Add 2 standard deviations. Then add a third one. All right. Questions on that right side before we go to the left side?
None at all.
All right. So that's what would be over here. 3905, 4410, 4915. And those will be your 3 values on the left side. So that's how your empirical rule will look using those 7 values, and then in between each one of those values would be those percentages that I mentioned already. And so if you had to use it, 34%, 13.5%, and all the rest of them, 2.35 and 0.15. So just re-emphasizing how you would find those numbers just in case anybody had a question. All right, so if we want to shade the region, all right, so shade the region that represents the proportion of full-term babies who weigh more than 4410. Now, we didn't have to do this in order to answer this question. I just did that just to make sure we remember the relationship and how we would calculate that stuff, just in case you are asked. But here, shade the region that represents the proportion of full-term babies who weigh more than 4410. So if you're going to do a generic shading, first thing you have to ask yourself, is this value less than or greater than the mean. Because that would dictate whether it would be on the right side or left side of the mean. If it's less than the mean, then it would be further to the left. You know, let's say if your middle is right here, then that 4410, if it's greater than your mean, will be to the right of that line. If it's less than your mean, it'll be to the left of that line. So 4410, our mean was 3400, right? So it should be to the right of your mean. And then if you're talking about more than, you're shading to the right. So that's what we would do. We would shade to the right of the mean. Let's say if we were doing, let's say we wanted less than. Same value, we're looking at less than. I'll just write like this instead of doing that. Let's go look. Uh, 4410 will still be in the same spot, but now shading to the left. Less than always represents to the left of. More than or greater than represents to the right of. So we're going to have, and you'll see that more prevalent in the next section, we're going to have a keywords and key phrases that's going to dictate whether we shade to the right or to the left. Less than, or anything that suggests less than, like below, colder, under. Phrases like that means less than or lower than. More than, greater than, hotter than, higher than, taller than. Anything that suggests more than, we're going to shade to the right. So we're going to have key phrases that's going to dictate whether we shade to the right or to the left. So questions on anything I've said?
Nope. I actually went through 7.1 real fast this morning.
Oh, okay. Well, that's good. That's cool. That's cool. That means you ain't need me. That means you could have taught the class today.
You show right.
So, any questions on anything before we close out this? Well, it's afternoon now. It's 12 o'clock. Before we close out.
It's lunchtime.
All right. So if you guys are good, I'm good. So have a great weekend. Be safe, and I will see you on Tuesday. I got some emails to answer. So if you did email me, I know I need get that taken care of. So I will be emailing you shortly. Outside of that, have a great weekend. Do I see somebody with a question?
Yes. Can I email you a question
Sure.
today? And I don't care when you answer it.
Sure. Yeah, most definitely.
All right, sir. Thank you. Have a
All
good
right.
weekend.
All right. You do the same. All right. All right.
See
No problem.
you.
Take care. All right. Take care. Get those moles.
Let me tell you about those moles real quick. So the place next door to us, there's an apartment complex next to my property.
Oh, hold on. Let me stop the recording.